Okay,
Okay,
perfect.
welcome
Okay.
everybody. Welcome everybody to our last Schubert seminar of the semester. We have Jennifer Morse from UVA, who will talk about non-symmetric Macdonald with a small side of Schubert calculus.
Thank you so much for inviting me. I always feel honored when I'm invited to anything Schubert calculusy because I know so little. But anyway, we'll see. I want to. I've been working recently with my collaborators on something called non-symmetric Macdonald polynomials. But what I wanted to focus on in this seminar is sort of a history of how I might have even been invited to this place, which is because of work with Macdonald polynomials that inspired some things in Schubert calculus. And so that's kind of been my own history. And now with the new non-symmetric stuff, I feel like there's a lot of interesting possibilities in terms of doing similar connections for that. So we'll see. It's a little bit too long, but we'll do what we can, and hopefully everybody will be able to get something out of it. Um, so everything is with my collaborators, Jonah, Mark, Anna, and George. So I'll just, before we talk about non-symmetric Macdonald polynomials, I have to talk about Macdonald polynomials. And before that, I'll just start sort of as a warm up with Schur functions. I kind of always do that so that, I don't know, it feels less scary for anybody who hasn't ever done it. So my first page is about Schur functions, which everybody is familiar with, hopefully. But I call it Schur functions the awful because it's actually the least inspired definition I can think of for a Schur function. I wanted to make sure to set the standards very low. So basically, this is indeed a way that you can define the Schur function basis for symmetric functions. It doesn't give much, but it says, okay, it's the unique basis that's defined by two properties. One, unitriangularity with respect to monomials, and two, orthogonality with respect to the Hall inner product, which is whatever, some inner product on the symmetric function space that's defined in terms of the power basis. None of the details are important. Really, you should simply be taking away from this that, okay, there's a basis that I can define with these two conditions, but what can we say about it? What do we know? Do we have a feel for what this basis might look like, what these functions are? So even to compute a simple example, you'd kind of have to do Gram-Schmidt or some sort of yucky or fun, depending on your point of view, linear algebra. So that's Schur functions the awful. And then the next thing, of course, is just to briefly review Schur functions the great, especially from a combinatorial position. Another way to think of them is that they're actually just sums of tableau. So write down all the tableau. Each tableau gives you a monomial, and you get the Schur functions. So one of the things that this slide tells you is that this definition, though it isn't obvious, constructs a family of symmetric functions that are actually positive sums of monomials. So anytime we see a positive sum, of course, as a combinatorialist, we want to count. So the Schur function is the sum of tableau. And so immediately you now know that the combinatorics of tableau is intertwined with Schur functions. And it's not just the definition. The very second question you could ask, second only to like, what is a Schur function, would be, okay, if this is a basis for symmetric functions, what's the simplest symmetric functions I've ever encountered? Z1 plus Z2 plus Z3 plus Z4 or whatever, right? Like that's just like a very simple symmetric function. You can take powers of it, it's still symmetric. And you can ask what happens if you expand that in terms of Schur functions. So you get some coefficients. And if you put that on the computer, it turns out that you'll find that those coefficients actually count standard tableau. So again, you see tableau coming up in questions concerning Schur functions and symmetric functions. One of the things I love about this example, even though it's the simplest symmetric function you've ever seen, is that it is an algebraic identity that is equivalent to the Robinson-Shenstedt-Knuth correspondence, which I will controversially say is the most fundamental result in algebraic combinatorics in the 1900s. It basically associates words, because this thing on the left is just a bunch of words, and on the right you have pairs of tableau. And so this identity gives rise to this whole theory that associates words to tableau that was developed over the period of, decades. And the sort of robust development that was primarily later Lascaux, Schutz, and Bourget, but early on Robinson, Shenstedt, and Knuth, led to the possibility of answering more difficult questions. So the next and last sort of combinatorial example is that once you kind of know how to work with words and tableau and Schur functions, you can go on to answer, for example, a harder symmetric function than the z1 plus z2 plus z3 is the Schur function itself. And so you can ask, what happens if I multiply Schur functions and expand into the Schur basis? And it turns out, amazingly, those are positive, and you can count them using tableau. Okay, so from a combinatorial standpoint, we love Schur functions because of these beautiful identities, and we can play with tableau and etc. But of course, the basis is notorious, not just for the combinatorics, but because it comes into other areas. So I'll give you two examples. Every example is pertinent to later in the talk, so you'll see them all again. So the first one is in representation theory, and it has to do with an SN module. Happens to be the module we call the harmonics module. So it's just, now we're not working with symmetric functions on this slide, just multivariable polynomials. And I want to take the vector space that's made up of the span of all the partial derivatives of the van der Maan determinant. So that's what this is. You can compute them and you can get however many there are, and then you take the span and you get a vector space. It's actually an SN module. If you take any harmonic and you permute the variables, you get a harmonic. So as an SN module, you can decompose it into its irreducible pieces, each one indexed by a partition, because that's what indexes the irreducible representations of SN. So if you're interested in an SN module, you really just need to know, like, how many times does this thing appear in the module? So how many times does that partition or the representation or module associated to that partition occur in my SN module? Okay, so Frobenius came up with a way to answer these, or at least study these questions, using symmetric functions. So this is just an SN module which happens to be multivariate polynomials. But Frobenius said, well, irreducible representations of SN are indexed by partitions. So if you map a partition to a Schur function indexed by the same shape and take the sum, then this result, this positive sum of Schur functions, is exactly equivalent to this decomposition by definition, just by definition. It's kind of stupid because you have to know this decomposition, right, to map them down one to one. But if you then say, like, okay, well, what is this symmetric function here? Can I understand it and then maybe understand its Schur decomposition? Then you can carry that back up to the module. And so this example, you may recognize from the slide that we discussed about the easiest symmetric function in the world. It turns out that if you take the harmonics module and you decompose it into its irreducibles and then map each irreducible to a Schur function, that symmetric function is exactly powers of z1 plus z2 plus z3, blah, blah, blah. So this, we already said, was the very manifestation of Robinson, Shenstedt, Knuth, and yet it tells you exactly how to decompose the harmonics module into its irreducible pieces. So I know that there's two of these because there's two tableaux of that shape. Okay, so that's representation theory. And then now, something I don't have to really spend much time on here is the other example, or a third example. We have combinatorics, we have representation theory, and then we have in Schubert calculus, the Grassmannian variety. And now you want to understand how to take intersections of Schubert subvarieties, and each one is indexed by a partition in a rectangle. So it turns out that the cohomology of the Grassmannian is can be studied instead as a quotient in the symmetric function ring. So it's like symmetric functions modulo some ideal, which I wrote there, but whatever. And the Schubert class in the cohomology can be identified with the Schur function. And if you want to understand how to take the product of the Schubert classes, then you have to understand how to multiply the Schur functions and mod out by that ideal. And the sort of beautiful thing about how this works is we already discussed that we know how to do this because we know how to work with Tableau and words. And the nice thing about this ideal is that it just kills Schur functions that are not indexed by partitions in a rectangle. So you can literally just work in the symmetric function ring, and then any guy that's not indexed by a partition in the rectangle goes away, and the others perfectly map. This Schur goes to that class, so the coefficients are the same. Okay, so my summary of Schur functions is that you can introduce them with an uninspired definition, but if you study them a little, you'll find that they do warrant the name of this like prestigious and wonderful basis. Combinatorially, it's absolutely the heart of Tableau combinatorics, and in representation theory, well, the one example I gave, there's many others, is that they're associated to this harmonics module, and you have the sum over words as Tableau, and then they also represent Schubert classes in the cohomology of the Grassmannian. Fine. Okay, so Macdonald polynomials. What are they? All right, well, it turns out that you can define them in the identical way that we define Schur functions in the uninspired way, which is, okay, now you're still working in symmetric functions, but your coefficients are in the field of rationals with two parameters, which we call Q and T. Okay? Other than that, what Macdonald discovered is that there exists a basis that can be defined by two things. Exactly the same unitriangularity as Schur functions, unitriangular in terms of the monomial basis, and orthogonality, but now it's slightly different than the Hall inner product. He's added this like rational sort of, that's a scalar, right? But it's a rational in Q and T. Notice that this little addition here, if Q is T, it goes away. So when Q is T, it's exactly the definition I gave for a Schur function. So all it is to get Macdonald's polynomial is to change the inner product so that you now have this little factor here. And that's Macdonald's polynomial. But of course, we already decided that that definition of Schur function was not exactly our favorite definition, but whatever, we have to take what we can get. So Macdonald computes some examples, just like with the Schur function. You remember we said, oh, when you compute examples, you see this beautiful sum of monomials and it's Tableau and yay, life is great. So Macdonald did that, and sadly, he did not see anything that looked even close to something like a sum of Tableau, because you have like, look at all these yucky negatives here. Not to mention you have rational functions, right? But he's happy to clear the denominator. You can clear the denominator, but you still have negative yucky coefficients. So that many of us would look at that and decide probably not to proceed, but Macdonald has a very high futility threshold, and he looked at it more closely, and he said, well, there is a way, first just get rid of the denominators, and then there's a way to like combine the yuckiness into a basis. It's not the Schur basis, it's not a power basis, it's not a basis you've probably worked with. I call it the funny basis because I don't even really know how to define it. It's like just not a basis you would ever really work that much with, at least in this community. But some funny basis exists so that you can combine the terms, and when you expand this Macdonald polynomial, or a scalar multiple of it, you get these beautiful sums of Q and T's. And he conjectured that the basis defined in this weird, uninspired way, in fact, has a QT positive sum of funny basis elements. Okay, so from a combinatorial viewpoint, you can say, okay, that's interesting. I wonder if I could prove his conjecture or figure out what those QT count, blah, blah, blah. But it's pretty hard, right? Because first of all, we use this definition up here, which is already very inexplicit. Second of all, we know that when you take the monomial expansion, it's really ugly. So, third of all, I don't even know what a funny basis element is. It's so hard. You know what I mean? Like, so how am I supposed to prove this? So, so Garcia had a proposal. He says, here you have this thing that's not monomial positive. It's yucky. And you want to prove funny basis positivity. If you instead take the Macdonald polynomial and just cross out the F and replace it with an S, okay? Then you have a different polynomial. It's obviously different because I've taken this yucky funny thing and replaced it with the Schur function. Now, whatever this new guy is, which he calls the modified Macdonald polynomial, whatever it is, it should be Schur positive if and only if Macdonald's polynomial was funny basis positive, because it's a very stupid substitution, right? So you might think, like, how does that help? Because I already had to have the funny basis expansion to replace it with the Schur function, right? So it does seem like it might not help. But what do we know about Schur functions? One thing we know is that each of these guys is a positive sum of tableau. There are positive sums of monomials, right? That was what we started with second. So that definitely means that this guy is a positive sum of monomials, a QT positive sum of monomials, because these are not. So that was one of the questions asked at the time. Could we come up with a better definition than using this unitriangularity to just directly define these with combinatorics? Because we know that there's the potential to define them as a QT positive something or other. So it took, I don't know, like 15 years or whatever, but Haiman, Hagelin, Lohr did do this. And in fact, there's a beautiful formula for Macdonald polynomials, very much like Schur functions. Macdonald polynomials are a basis for symmetric functions, so they're indexed by partitions. But what you do is you take each row and you map it over to a tuple. So this is like a list of rows, one for each in this partition. And then you also allow not just this list of rows, but any wiggling of those rows, which we call ribbons. But so like you take this guy and you're allowed to wiggle it into any skew shape that looks like a ribbon. So the Macdonald polynomial is, and then you put tableau in them, literally their usual tableau. So you sum over all the possible tableau you can get by filling tuples of these ribbon shapes. So that's what this is down here. It's a simple example. And these are all the possible tuples of two ribbons and a one box. And I fill them just with usual semi-standard tableau. Well, it's infinite, but whatever. So each one, just like Schur functions, gives me a monomial, just the weight. Of course, it's a QT sum. So each one of these guys contributes some QT power. The T is related to inversion. So you just look at the numbers on a diagonal and count how many are inverted. And then there's a weird off diagonal thing also, but whatever. It's basically like inversions. So that's what ind is. And the arm says, well, if I look at this tuple, how much did we wiggle the shape? If you take this tuple, the arm is 0, but when you start bending your arm, you get a contribution of Q. It's not important the precise details, just that you understand that Macdonald polynomials, modified Macdonald polynomials, are quite simple to write down. You just write down tableau and then you compute the inversions, you compute the arm wiggle, and you're done. It's a QT sum. That's great because at least that seems a lot easier to approach Schur positivity than this funny basis stuff. Turns out it actually wasn't that easy, but at least it gave the illusion of it. So anyway, so that's good because now we don't have to talk about any scalar products or anything. We can literally just write down a Macdonald polynomial. Okay, but what about the fact that the real conjecture was this was supposed to be Schur positive? And then going back to Macdonald's, it's funny basis positive. So what you really want, not necessarily just this beautiful combinatorial formula, but you want to know what the Schur coefficients are. Well, okay, that is harder, but it was actually Garcia's idea to switch the funny basis to Schur was really a lot deeper than just, oh, well, then I'll have a monomial positive thing. He was thinking about the harmonics module. So remember, the harmonics module was this linear span of the partial derivatives of the Vandermonde. And we saw that if you mapped an irreducible to a Schur function, well, we saw it without this Q. It was just the sum of Schur functions with tableau, and it related to words. You can put in extra structure. Here you have an isomorphic copy of this module, but of course, the actual harmonics in here don't have the same degree as the harmonics in there. These are degree 2 and those are degree 1. So if you want to know more than just, oh, there's 2 isomorphic copies of this, if you want to know, like, I have 1 with polynomials of degree 1 and 1 of polynomials of degree 2, you can actually get that information by simply mapping still the Schur function to its shape, the irreducible to the shape, but then the degree 2 gives you the power of Q. Okay? So now you get a Q positive sum of Schur functions. So anytime you take a graded SN module and you take an irreducible and map it to Q to the graded piece times that Schur function, of course, you'll get a Q positive sum because you're summing the irreducibles. So this picture with the Q was completely worked out when Macdonald polynomials came along. It was already known, and in fact, the Robinson-Shenstedt-Knuth worked not just to prove that words went to the tableau, but that the inversions, which was what you get when you do this, can be mapped to charge. So this was sort of like a very, very complete and beautifully well understood picture. The other thing that was understood when the Macdonald polynomials were introduced is that this was a special case. Macdonald polynomials have a Q and T, and the modified Macdonalds, right, they look like this, QT positive sum of Schur functions. And in a special case, you actually got exactly this. So the idea in Garcia's head was, if we want to prove Schur positivity of the modified Macdonalds, we think they're QT Schur positive. So is there a module that now has a bi-grading? So before we just had the linear spans of the Vandermonde, these were polynomials in X. If we have something with polynomials in X and Y, then if you record, the Q power could record the degree in X as before, and the T power could record the degree in Y. So the same map from the irreducible to a Schur function, but now attached to a QT monomial recording the bi degree of the SN module. And that's a question that Garcia and Haiman worked on. Is there such a module? We know that in a special case, it's this harmonics module. And they proposed one, and eventually Haiman was able to prove that, in fact, the modified Macdonald was its Frobenius image. And what they did was they sort of beefed up the Vandermonde determinant to have X's and Y's, and there was one for each partition. So using the linear span of beefed up Vandermondes in 2 sets of variables, they got an SN module. The symmetric group acts on the X variables and the Y's simultaneously. And Haiman proved that the Frobenius image is this modified Macdonald, which by definition means that you have Schur positivity, because the Frobenius image is a sum of Schur functions reflecting the decomposition. So that's amazing, and that was done around the same time as the combinatorial formula, actually. But what's still open is, okay, you know that there's one of each of these guys for each tableau. And you know it's Schur positive now. So you know that there's just a QT monomial for each tableau. The Haiman-Hagelin-Lohr formula says the modified Macdonald is the sum over the tuples of tableau with arms and inversions. Is there a combinatorial way to prove what these coefficients are by associating some T power and Q power to each tableau? It's like, you know, it has to exist. But anyway, it's still open. So that's a hard problem. Obviously, one that is near and dear to my heart, so near and dear to my heart that I have been working on it since I became a mathematician as a graduate student. Obviously, that doesn't speak very well to my success as it is still open, and that was in the 90s. Anyway, so what was I doing in the 90s? I'll tell you about that. I was like obsessed with this problem. It's a beautiful problem. Of course, it wasn't even a theorem yet that you could do it, but we do know that for each tableau, you should be able to find a Q and T in the modified Macdonald polynomial. So we know that, and we know that in a special case like this one, oops, I just hit the eraser. In this special case, you only have one parameter, because that was the harmonics module case, and you know what it is. It's called charge, and I can take this tableau and I can compute this phi very easily, thanks to Lascaux, Schutz, and Berger. That's so much to know. And it seems so like you could definitely answer this question. Okay, so of course I sat in the corner, tried. And so in the late 90s, I was with Alain Lascaux and Luc Lapointe trying this problem. And while we didn't solve it, we did study these tables a lot, and we made an observation. So the observation is like, this guy only involves T, and he's pretty easy. Immediately, all the others have T's and Q's. They all, or at least all the others have Q's. Here you have only T's. But what we noticed was if you can look at not just the first one, but the first three. All these guys which are indexed by partitions with no more than 2 columns. So restrict yourself, just ignore this stuff. What we discovered was that, remember, we felt like T sums of Schur functions are easy. It's just a singly degraded something, it's charge. And we saw that if you looked at that set, there were these sums of Schur functions involving just T's. And then the coefficients were still positive. Okay, and so one for each of these shapes. One of these bubbles for each of those shapes still had positive coefficients in Q and T. So we were like, oh, wow, maybe we can figure out what this guy is, and then this is easier. But of course, it's a little bit disappointing that it only works for 2 bounded shapes. So that's like special case city. But what we observed is and it doesn't, right, you see that there's this Q here. That guy really ruins it for us because this is definitely not here. So you definitely can't just take the 3 shape. So what we discovered though was that if you want to consider all of the guys with at most 3 columns, you have the same phenomena, but it breaks apart the 2 shape case. So here you have this bubble for just 2 shapes. When you go and add another Macdonald, you now get smaller bubbles that are making up the case for the higher level. So what we saw experimentally can be summarized here, which is that for each K, and that'll be the width, how wide you want to take your Macdonald. So you're going to take the span of Macdonalds where you only have shapes no bigger than K columns. If you do that, they decompose into some other elements, positive sums of T's. So these have only T's in them. That's not a very good color, but that's a T, right? So it's like there's a basis for the space of the span of this restricted space of Macdonald's that involves T positive sums of Schurs, and the coefficients are still positive. And they are embedded in each other. So that was like the big conjecture when I was a graduate student. And again, we thought this is awesome because we'll just figure out what these guys are, no problem, and then we'll just figure out what the coefficient, these smaller coefficients are. So then, after 2 decades, we couldn't even find a definition where we could prove almost any of this. So we said, what are these things? Like, what is the definition of this thing? It's supposedly a basis. It's just a T positive sum of sure's. Like, how hard could it be? Right? And in our original paper, we proposed a definition. This one. The branching is the phenomena that the K version can be decomposed positively in terms of the K plus 1. Okay? By our original definition, we could show it was a T positive sum of sure functions. We couldn't show it was a basis, and we couldn't show anything else. So then we said, what about a different definition? What about a different? And like various people tried and introduced different definitions. You can see that like at some point it was even so sad that we picked up several collaborators and proved even less. So like over time, right, the situation didn't really improve at all. It just like was stagnant. Lots of different ways to look at what we thought they were, but none of these could be proven to even be the same as each other. So it's like really, really a problem. So you're thinking, you spent 20 years on that and like you really got nowhere. And so since I'm still in math, obviously I was doing something else. And so what happened was Luke and I decided, okay, well, like, what if we let T be 1? Can we maybe it's easier to work with these guys when T is 1. So again, the guys are these things coming up in Macdonald polynomials. When T is 1, they're just sums of sure functions. Well, it turns out actually T is 1 is not that much easier. However, something amazing happens, which is that when T is 1, the linear span of Macdonald polynomials, so now, or the linear span of these K-sure functions, simply becomes this ring. It's a ring. Otherwise, it's not a ring. And it's the ring generated by H1 up to HK, E1 up to EK, however you want to think of it. And so we found a definition where we could finally prove like at T is 1, you have a basis for this subring. But what was really kind of exciting, and probably the reason that we stuck with it, was that when T was 1, since it was a ring, you could multiply them together, and then we saw that the coefficients in terms of that basis were positive. So that was like, okay, now we're really starting to see a lot of the phenomena that the sure functions have, and we kind of have a responsibility to like work this out. So I do have a natural stopping point in a couple minutes. Is that okay? Okay. So briefly, before we rest, it turned out that we could relate when T is 1, these, we call them K-sure functions, to quantum cohomology. So as far as I understand, quantum cohomology is a Q deformation of cohomology. So as a linear space, all you're doing is thinking about cohomology and taking your Schubert classes and putting Q coefficients as a sum. But the product is where it becomes much trickier. One way to think about the quantum cohomology structure is that the ring structure is defined by the structure constant. So we say, let's define a product by saying if I take these two Schubert classes and multiply them, their expansion coefficients are going to be given by this thing called a Gromov-Witten invariant. So some like complicated numbers, whatever, you guys know way more about them than I do, that especially at this time were very, very difficult even to compute, were used to define, well, it was an associative ring, and they called it quantum cohomology. So in the case when you take the Grassmannian, this is actually isomorphic again to symmetric functions modulo an ideal. I always feel a lot better when we talk about algebra. So anyway, so for me, like I perk up immediately, but sadly, this ideal is pretty yucky, right? Like it's not like the ideal that you use to get the cohomology of the Grassmannian. You now have like this stuff in there. So you could take a Schubert class and say, okay, I'm going to map it to a sure function, and I can get the product by taking two sure functions, multiplying and mod out by the ideal. Yeah, you can do that. But a sure function modulo this ideal is not nice. It's not easy to do that. It's hard. The ideal doesn't have a good description in terms of regular sure functions. So what we discovered, though, is that if you use the K-sure functions, it works exactly the way it works with the Schur functions for cohomology of the Grassmannian, where when you take a K-Schur function product and you expand in terms of K-Schur functions, that if you map it down modulo this ideal here, anybody who's not indexed by the nice shape is 0, and otherwise you get exactly one positive Q power of a Schubert class. So that means that these coefficients are exactly these coefficients, which we said were these Gromov-Witten invariants. So this is like, mind you, I didn't know very much at all at this point. I know only slightly more now. But anyway, so I was like, that's awesome, obviously. I'm not going to lose my job. But also, I was really curious because it was like, but there's all these Schur functions, right? For every partition that doesn't have a width bigger than K, I have a K Schur function. And so many of them go to 0 when I work here. And I was talking to Mark Shimazona, who is awesome because he's like knows a lot about Macdonald's and about Schubert calculus. So he's like my perfect resource. But anyway, so I was like, why are there so many of these? What could the rest of the coefficients be? And so that's when he told me about all this stuff with Peterson, and he talked about the affine Grassmannian, and that apparently it was known that if first of all that you have a homology, you have a ring structure on the homology of the affine Grassmannian, and that this is isomorphic to the quantum cohomology of flags. Remember, what Luke and I did was only the Grassmannian. And so you have this setup where you can study quantum cohomology of the flags, which, by the way, means you can also ask the question about how to multiply Schubert polynomials, which is even when Q is 0, we don't get it very well combinatorially. But anyway, so you have this isomorphism from the homology of the affine Grassmannian of SLN, but it was known that that was isomorphic to none other than exactly this ring that we had been studying because it was the K-Schur function were lying a basis for that ring. So then, Mark and I decided that it had to be that the K-Schur functions were representing these Schubert classes in the homology of this affine Grassmannian. And Thomas Lamb, who was like a whippersnapper at that point, like immediately proved it, that when T is 1, this definition that Luke and I gave for K-Schur functions, just when T is 1, could be representatives for this affine Grassmannian. So this is my summary, and then we'll stop. So, I mean, unfortunately, there's still a lot more, but we'll at least stop for a minute. So the summary of modified Macdonald polynomials is that you have this basis defined in what I think is an uninspired way, right? Very difficult to get a handle on it. But when you modify it using this Garcia modification, you get this beautiful basis that's combinatorially a sum of tableau, ribbon tuple tableau, involving inversions and stuff. You get the Garcia-Haiman modules, so it has this beautiful representation theoretic interpretation. And of course, the proof required geometry way beyond my comprehension, that Haiman had to use Hilbert schemes and stuff like this to prove that. And then finally, the last piece is that we found these K-Schur functions by studying Macdonald's and preserving this positivity and getting this like branching phenomena. And when T is 1, you see that they are these representatives for the affine homology of affine Grassmannian. Okay, so would you like to take a stop now?
Yeah, yeah, this seems like a really good time. Maybe we could stop the recording and